who they are. Now they put out who they are. But it's not we show. So it's still okay, you know, you still have if it's local, you can still write conservation law of that type. Yeah, that's right. And then you just write so the problem is in here, potentially, right? And then you have constraints on the beta. So you have to make sure that this makes sense as a probability measure. That gives you constraints in the beta. So you have a space of beta. It's not anything not everything. It's a space of betas that work. Here, because they're positive, then you can take your space of betas to be positive. Questions? Sorry. No, this doesn't work. Escape. Okay. I think. Very good. Thank you. I have other questions.
Just curious about when you say it's a reduction in number of degrees of freedom.
Yes.
So, but I mean, roughly speaking, you have as many Q bar, beta as a C bar.
Yes, yes.
And for integrability, you have as many Q bars as number of degrees of freedom.
So not quite. It's interesting. Yes, almost actually. That's why integrability is very special. So you lose some information. You know, kind of you lose half of the information, the phases.
Yeah. Okay.
That's it. Yeah. But you have a huge amount. So for integrability, you would have infinitely many of these Qs, and then it's not a big reduction, but still it's a bit of a reduction, and it's what's happening at large. The hardware models is actually integrable. I don't have to take a set of rods with just two velocities. I can take a distribution of velocities. Then I have as many conserved quantities as I have velocities. And this is the typical expression of integrable models. Okay, but then I just want to continue with this just a little bit. So important point is that I have as many equations as I have betas. Stated. So in principle, this determines the dynamics of these betas. And once I know the betas, I kind of know everything, right? Because if I assume this, then I can calculate any observable, local observables using these betas. It's enough. So I know everything. I know every local observable, average of local observables, under this assumption. Okay. So it's really, this is a reduction. Okay. Now, what this equation can be written in different form. You can write it in a quasi-linear form where you just take the derivative of J respect to Q, the Jacobian there, so it's linear in the derivative of Q's. And then it really looks like equation for these Q's, and these Q's are your reduced degrees of freedom, your fundamental variable. Average basic in space-time. For the hardware models, these currents have been evaluated exactly in terms of the Q's. So this you can calculate it. It's a small calculation. It's not so difficult. So yes.
I missed something. Did you say that you determined the beta, the maximum T, the betas?
Okay, let me back. So I was a bit quick. So the betas, according to Hydro approximation, I don't know what they are. It's just some betas, right? And this is an equation for these betas, dynamical equation. So this is an equation for Q's as a function of beta and J as a function of beta. So it can be said as a dynamical equation for the beta. So once I know their initial value, in principle, I know their values at the end of time. In this way, I determine it.
So you can back out what the betas are for evolving that system.
Yeah, exactly. But then actually it's not very convenient to do this map back from the Q's to the betas now. That I can just take the Q's. So I can say beta is a function of Q by inverting that, and then J is a function of Q by putting that here. Then I have J as a function of Q's, and in hardware, this is the result. Yeah. So in general, this is what's expected. You write things function.
Are you assuming that the Q's and the J's are functions just of beta, they can be functions of the derivatives of beta?
So this is a very good question, thank you. Here, the assumption that I'm making is just function of beta, and the very specific function of beta, the one obtained by the Gibbs state. But this is incorrect in general. I mean, it's correct at a larger scale, but there are corrections. And then the J's in general with hydrodynamics will be assumed to be functions of beta and their derivative in some kind of gradient expansion. But I will not discuss. And then the what how they depend on the derivative of beta. This is a specific relation, and it's there's Kubo formula to evaluate this function. There's a lot of other questions. Okay, so this is hydrodynamics for the hydrods. When does it? I mean, fundamentally, what are these Qs and when does that work? I mean, the whole thing works pretty well if we know what the given states are. What are the given states? This is actually not very easy question, in fact, right? So put out the conserved quantity, but then what are all the conserved quantities? What do I mean by all the conserved quantities? This is a kind of fundamental question, especially in okay. So in general, the states which are relaxed are those that cluster in space and are space-time invariant. So when you have a given state, it's a general result, given state of local Hamiltonian, that if you look at correlation functions of local observables that are well separated, then this correlation function decay quickly, decay. And of course, it's invariant of the space-time translation. Well, this is kind of a fundamental property of these relaxed states. You cannot ask for that. The idea is that any state that clusters in space, that is space-time invariant, is a good given state. There is some conserved quantities and some form exponential beta qi and by. It's kind of fundamental, more fundamental definition of relaxed state. Okay? What are these conserved quantities? Well, they are, it can be anything, right? So it's important that we have in particular some local density of this type to write our hydrodynamics. So the fundamental principle, in fact, is that the conserved quantity should be some observable, whatever is observable, quantum mechanics operator, or just observable. But it should be such that it is extensive. So you should be able to write it as an integration over X or something local. Actually, extensive has a more fundamental meaning. So extensive would be, and it's kind of equivalent to being able to write it as an integration over local density. It means that its average square, its cumulant, should grow like volume. Not more than volume, and not less than volume. If it grows less than volume, then this is just a wrong conserved quantity. You just take it out. It's not involved in hydrodynamics. If it grows more than volume, also not involved in hydrodynamics. In fact, it will be involved in the corrections, the derivative. So those are both volume. And if you look at this kind of conserved quantities where you integrate over X, that grows like volume. The cumulant will grow like the volume. Okay, so and it turns out that if you take this condition, you can construct a complete space from the Hilbert space of that, and then you have a complete accurate definition of the complete space of conserved quantities that you should write, that you should use. Okay, but this is a bit formal, and I'm not sure how to make that. I will not say more about this. The picture that we have reduction degrees of freedom is that there's some kind of, let's say, Newton equation, evolution, and all that, but we just reduce degrees of freedom to subset of states, which are the given states. So we do some kind of projection, but actually physics does the projection. And so the evolution, instead of going kind of everywhere where the observable take all kind of possible values, no, they just take very specific values inside some submanifold. And these conserved quantities are just a tangent to this. Okay, so this is kind of the structure. But now I want to do integrable models. Right? People ask about that. Of course, there are infinitely conserved quantities. So I have all these QIs, these are called generalized given ensemble. I write this infinitely equation, conservation equation, and these are my hydrodynamic equation. Right? And that's it. Hydrodynamics is very simple. Just write all of that. Of course, it's not so. I mean, the crucial bit is this current, right? There was a question, I have to evaluate things as function of beta, right? So Q as function of beta, J as function of beta, or maybe J as function of Q. I have to evaluate these things. And this is a difficult thing. Right? In integral systems, how you do that? In any system, how you do that? And here I have to evaluate infinitely many of them. Right? So it's very difficult. But in the end, it's not too difficult. Okay? And as an example of the hard rods, where all these conserved quantities, where you just take that the function theta is my parameter, being equal to Vn, where these are the velocities of the rod in the distribution, these will be conserved quantities. So, okay, so how do we do that? Well, we have to, the physical principle, and I'm not going to give a derivation, no proper derivation here at all, it's not mathematical, but physical principle. Physical principle is based on scattering theory. So what does it mean? So in integrable models, there is a concept of a factorized scattering. Means if you send a lot of particles or solitons or whatever stable asymptotic objects you have in your sense, they're far from each other. You send them towards each other, interact, a lot of stuff happens, and then they go out. As they come out, you find the same thing, the same soliton, the same particle with the same velocities. Just that perhaps the positions of these trajectories will have been shifted a little bit like this. You send two particles, they interact, and then position has shifted a little bit. Function that determines the shift. But these shifts occur in a factorized way, meaning that the many-body scattering, like this one, can be seen as if the particle had interacted two bodies at a time. So the shift of this particle is going to be the sum of the shift due to interaction with one particle and interaction with the other particle, just a sum. So this is factorized scattering. This equation is a Yang-Baxter equation. In fact, in this context here, it's a very simple example of that, but when you go to more integrable models, it becomes a rather non-trivial equation for scattering matrices, and there's a lot of theory about that. But okay, factorized scattering is the Now, why is this useful? I was talking about constant quantities and hydrodynamic equations. Why is factorized scattering useful? Just as an example, in the hydras, the scattering shift is just the length of the rod because you follow the velocity, and when two rods hit each other, they exchange the velocity. So I follow the black line, and indeed, so I have a shift of -80 in my station here. For solitons, is a soliton shift, like Now, why is that useful? It's useful because in integrable system, what you can do to determine the state of the fluid cell, like this generalized Gibbs symbol without the constant charges, you can just forget about the constant charges. Don't fully forget, but forget about them, and determine the locally relaxed state by doing a so-called time of flight experiment. Meaning that you have your fluid, and people actually do that in experiments, right? You have your fluid, particles that interact, and then you see the fluid has relaxed somewhere there, reached some generalized Gibbs symbol. I can just take out the fluid and put it in the vacuum and let it expand, and see what are the velocities of the particles. If the system was not integrable, yeah, what you would see is essentially the black body radiation. Right? This is what black body radiation is. You see that you will see a distribution of particles according to Gibbs. But because this is integrable, there are many conservation laws, and because the scattering is factorized and preserves the momentum, what you will see is some distribution of momentum. But you can see any distribution of momentum. So you extract, you take your particles, you put them on the vacuum, you let them expand, and then there's a whole function rho of theta that determines what the state is. And any function will do.
Extraction, you assume that theta's are non-zero.
Yeah.
That not punish, because otherwise you would have to have a bound state.
Yes. So the bound state is not that. So in this construction, this is the really simplest picture possible. But indeed, you can have so what you have to think about is what are the possible asymptotic degrees of freedom. If you have bound states, then these will come out as possible asymptotic particles, and then you're going to have the density of such bound states. And then you have to take this into account. So my theta here is very simple; it's just the momenta. But in general, you have a spectral space, right? Not just the real line. It's more complicated. It can be real line. It can be a direct product of real lines of the various particle types, various bound states. It can be C2, like in NLS, right? Where you have essentially a continuum of possible bound states. It can be more complicated than that. Here I'm assuming really simple situation. Okay. But this is a situation, is because of all the constant quantities, you can have any function rho of theta. So now this rho of theta, which is the density of asymptotic particle in theta neighborhood, this is your actually positive constant quantity, constant density. Okay. It's a density because you can do that in fluid cell by fluid cell, and you will find different rho of theta. We define this rho by saying that if you have a fluid cell of length L rho d theta is the number of particles you will observe in a d theta interval. It's a well-defined quantity, even experimentally. region. Okay. Okay, and then the whole thing in the in generalized hydrodynamics is that once you know this rho of theta that tells you the distribution of particles, in principle it tells you the betas. There's a relation between rho and the betas in the GE. I'm not going to show it to you, but there's a relation. And then you can calculate the currents. And this is kind of there's a lot material on that, but it turns out that the result is relatively simple. Just going to show you the result. It turns out, and it's interpretation, the currents can be evaluated as function of the rows. We wanted the J is function of Q, so the current J is function of the row. And it turns out, so we can write them in this way: some V effective times rho, some velocity times rho. Imagine that every particle would go at some velocity, and just velocity times rho. But the velocity is not a trivial object; it's something that depends on the rho itself. So this is a nonlinear equation of state. Given the distribution of particles, then you know the currents of the corresponding constant densities. You just have to evaluate them. And this is the equation. The effective velocity satisfies a linear integral equation. This is a result of calculations, and actually I should apologize to the absolute master of soliton gas, getting the L for not citing. This is in the quantum context. Of course, we obtained that much before, like 10 years before, something, unbeknown to all of us. So of course, in the soliton gas, this was obtained before by different methods, by finite gap theory. In quantum models, then it was obtained by also a variety of methods using crossing symmetry in quantum field theory, using form factor expansion, and using algebraic Bethe ansatz. So the last one is kind of the most accurate general proof using algebraic Bethe ansatz. And it really tells you what the currents are for these density of a synthetic body. Now, it has a nice classical interpretation. I should say this is true in classical, in quantum models, in soliton gas, particles, spins, whatever. It's always the same equation. Nevertheless, it has a very nice classical interpretation, purely soliton gas interpretation. And the interpretation is that you imagine that you have a particle that goes around in a gas and then interacts with other particles, right? And we said that the scattering is factorized, so let us take that kind of very seriously. And this particle goes around in the gas, and it just factorize all the scattering to two other scattering. So what's happened? Well, it kind of displaces a little bit in some velocity. Theta now here are my velocities in simplified construction. Then it kind of maybe interact. I can represent this by, say, they get stuck each other for a while, they interact, and come out, and there's a shift because they got stuck. We're going to time delay. And then the particle accumulates a lot of shifts. In fact, for a macroscopic length, it will accumulate a macroscopic number of shifts. So that actually changes the distance it has traveled in time t in a macroscopic way, in a significant way. And you can just make a simple argument, right? So the probability that it hits a particle of kind of a spectral parameter alpha is rho alpha times the difference of velocities that particle between particle theta and particle alpha. If they are the same velocity, they would never hit each other. If the velocities are very different, they will hit each other a lot. Right? So this is just the probability, and this is the amount that is shifted every time. And then you integrate to rho alpha, and that's the difference.
So at this stage, what do you know about phi?
So phi is got to be determined in your value microscopic model in some way. So, and phi actually is a simple, I mean, like for the hard world, you just look at two particles, it's minus A. Phi doesn't matter. In general, you take your, say, even the quantum model, you take just two particles and calculate the wave function, and then shape it, then calculate just two particles. Or you take a soliton, KDV soliton, two solitons, you know the explicit solution of two solitons. So this is a two-body problem only, usually easy to calculate. But to calculate it is easy, then to prove everything is very difficult. Calculate the fundamental quantity. And indeed, so what are the quantities we need? So phi is the thing that determines the model, and kind of nothing else. Well, actually, there's phi and the spectral space, right? Maybe the spectral space is just real line or something more, but fine spectral space, determine the model, and nothing else. And once you have the integral model as determined by fine spectral space, you have this hydrodynamic equation. Then you may think, maybe there are many different integral models that have the same two-body shifts. Yes, and they will have the same hydrodynamic equation. So many different models may have the same immersion parameter at the earlier scale. Because it's just few data that. And then, so I just write the equation. This is dx of the density plus dt of the density plus dx of the current equals 0. That's the equation. And this is the generalized hydrodynamics equation. It's a non-linear equation for a rho, because this VF depends non-linearly on rho. It's like a differential integral equation, because VF depends on rho at different spectral parameters. This integral equation being okay. Question about it? Yes.
Do you have any thoughts what you would do if the phi was 0? Do a calculation.
If phi is 0 here, yeah. So then this simplifies to a Liouville equation for free particles. So if you have no interaction, you get just the equation that tells you that you preserve phase space volume.
But you wouldn't think to try to go to higher order instead of the microscopic calculation.
So you can try. I mean, you may have higher order corrections in some way. You do have higher order corrections in some model where you may have phi equals 0 and yet some higher order corrections. Yes. And there will be this is just a mistake. Something else can happen. So phi equals 0 is not the only. But what it says is that if I take free particles and I want to construct the order hydrodynamics of free particles, I can do it, and I just get the Liouville equation. Especially in phase space. Another question. So this is it. So this is kind of a universal equation that apparently works for every many-body integrable systems of many types, of alpha small types. Essentially, in that form, it always works. That the true fully rigorous derivation, I think soliton gas is a very sturdy derivation using finite gap solution, but a rigorous derivation in terms of statistical mechanics, random distribution of fields and all that, and that gives this equation that there isn't much. The only true fully rigorous one is for the hard rods, as far as I understand. But it's getting there, especially soliton gas theory has a lot of strong mathematical structure, so it should be possible to actually write that. Yes. Now, so it is possible to rewrite this equation in many ways. One way, which has been quite fundamental both in soliton gas theory and in the GHD as applied to many-body quantum model, is to rewrite in terms of Riemann invariant. Now, this is quite surprising. So in general, a hydrodynamic equation, dtq plus dxj, can be written in quasi-linear form. dtq plus a dxj is a handwritten. Then you may want to diagonalize this A matrix of Jacobian. Have something dt something plus velocity dx something that just doesn't mix up the various modes. And it's not always possible, but it turns out that for GHD it is possible. So here's the transformation. It's a very simple one. We define this n as being this rho divided by a certain denominator. And come back to what this means. 1 plus integration phi rho. Then you do a bit of calculations, 5-line calculation. A bit magical, things work really nicely. And you then get an equation that's similar to that, though the effective velocity is outside with the same theta. So now this is a diagonalized form. This is a transport form of the hydrodynamic equation. Ptn plus Vf dx. That means that Vf are the hydrodynamic velocities, and that means that this n can be evaluated simply by tracing the trajectories of quasi-particles. Trajectories are just curves that are parallel, whose tangents are the effective velocities. So tracing trajectories following the effective velocities, I'll do it times 0, and the n takes that value. So n at time t takes exactly the value n at time 0 along these trajectories. These trajectories are the characteristics. So essentially, you have kind of a solution by characteristics for this kind of for the GHD just by this transformation. Now it's not quite a solution because the effective velocity is a nonlinear function of n. This is still highly nonlinear. It's kind of diagonalized form, but still highly independent. This n has a meaning in the quantum context when you have an integrable model, quantum integral model of fermionic type. N is the occupation function. But now it's between 0 and 1. So it's the occupation of fermion with an available space and all that. So in free fermion, N is just occupation function. The interacting fermion is equivalent of occupation function. And satisfy this question. Yes?
I'm just confused about in what sense these are human invariants. So this is a scalar equation coupled with an equation between these transformations and what is the
So in the sense that what I'm talking about human invariant, right, that if you have a hydrodynamic equation dt qi plus aij dx qj, this is in quasi-linear form, you may want to diagonalize. So you write qi is some function of all the n's. Okay? You put that in here, and what you find is that the Jacobian of this transformation transforms A by similarity transformation. So you get then the new A becomes Jacobian A, Jacobian inverse. Okay? Then you may say, maybe it's possible to find transformations so that Jacobian diagonalizes A. A is diagonalizable. We know it's diagonalizable, but it's not always possible to find something to do this. If it's possible, then what you get is dt ni plus some velocity, say vi, that depends on all the n, of course, which are the eigenvalues of A. Eigenvalues of A, dx and I. And this is what I call a Riemann invariant. Measures by terminology. This n is a Riemann invariant. If you can do that. Make sense?
Maybe another version of the question is you've written one of the equations in diagonal form, but it's coupled to another equation, and you diagonalize all of them
Yeah.
together.
So maybe what you're asking is, okay, I've written that, but of course I haven't gotten the solution yet because it's coupled, right? I mean, VF is not diagonal in the M. Indeed. And okay, I'll come to that. How we kind of not quite decouple, but get some kind of solution, more explicit solution. But yeah, in this sense, it's not completely coupled. So it's really still highly non. Other question. Okay, so now, sure. Well, okay, this one can go in experiments and check this equation. There's an experiment where you would have an atom chip with some rubidium atoms at very low temperature, let them evolve, and they are described by a model, which is integrable. And you can actually see, you can take picture. This is like an actual experimental picture. Picture of these atoms, every pixel we see about 10 atoms or so, they assist in that experiment. And you can compare conventional hydro with GHD, and the conventional hydro is a dotted line that really doesn't work, and GHD is a nice smooth line that works very well with wiggly line, which is the experiment. The GHD works. Well, it's not a proof of GHD, but if you go in the experiment, it actually does describe the real world. Some other equations do not describe. Okay, now one can add force term. In this experiment, we did add force, external force term. How you do well, you remember that this is an integral model in there's a hierarchy of times. So all the higher charges are higher Hamiltonian. So I didn't need to take the Hamiltonian, to take any of the charges. There are all these times settled with that. And of course, then they're all, I say the concept quantity, these things are all in involution. They are proper Hamiltonian with integrable. So for every time Ti, there's also a corresponding set of currents, Jik, for all concept quantities K. So it's not just the Ji, it's the Jik. There's a lot of thing, right? Now, so my Hamiltonian, I can take a general combination of these things, and then I have kind of a generalized version of hydrodynamics for these higher Hamiltonian of the hierarchy, where the currents are just linear combinations of these kind of currents associated with higher Hamiltonian. Okay, I can do that. And the GG equation is a simple thing, is trivial. The GG equation takes the same form with the effective velocity now being, well, instead of the theta that I had there, is the group velocity. D theta of E, where E is some kind of energy, which takes a linear combination of all these HI are the one particle values of the concept quantity. So if you have a soliton gas, HI of theta is the quantity, is the value of the concept quantity I that is carried by soliton theta. Soliton goes around and carries its own energy, its own momentum, its own higher energy. So this is the example. Now you can do further and consider space varying Hamiltonian density. So this is not integrable anymore, by the way. Now this is a Hamiltonian, which is not integrable because you have you integrate over x, you put your constant density, but you have a c of x there, some function of x. You can imagine you have your many body system that you couple to some external magnetic field, and that's space varying, for instance, that experiment. But if this c of x varies only on large enough distances, you can still write hydrodynamic equation. Even if it's not integrable, you can still use the GHD for a integral model. And it turns out that there is actually a general equation, a general Euler hydrodynamic equation, which I not derived that involves this CI. And in the end, the GHD equation takes the form dx vf rho plus d theta af rho, where a is some kind of effective acceleration. And quite surprisingly, effective acceleration is the same form as effective velocity, except instead of having d theta e, you have dxe. So here is dxe, previously I had d theta e. It's the same thing, except you take the force corresponding to that energy instead of the group velocity corresponding to that energy. This is the energy corresponding to the same. This is the equation for with the external force term, and this also has been checked in the experiment at the graph there. Now it's interesting because now it becomes a two-dimensional, 2 + 1 dimensional equation. It's a conservation law because it's in conservation form, right? But for something that lives in 2D x theta in spectral space, in spectral phase space. And you can kind of do the numerics of that. This is for the linear model with some potential. You start with say practical potential with some blobs of particles of rho, then you evolve that. This is 2D, right? This is rho of x theta. And it evolves and kind of does that kind of things like fluid. Actually, GHG is a 2D fluid. Okay, so this is one thing you can stand and you can check also in the experiments. Now, what is the structure? To gain a bit more insight in the structure of this equation, this is what I'm going to do now in the last few minutes. It's good to do some reductions. Now, next talk, I think there will be a different type of reduction, which is called polychromatic reduction, that people have worked on context switch and gas. But here is another different reduction, very simple one. It's kind of coming back to the hadrons. You have your GHD equation, and you can ask about structure. Now that's what you can look for. Very special type of reductions. I call this atomic reduction, where you look for a density that is concentrated on fixed x and thetas. Xi of t, theta I of t that depend on time. Now these becomes like trajectories, right? You have trajectories xi theta. T is xi theta. So x theta is like a phase space. You have trajectories in phase. Look for solutions of that type. Okay, you can do that. You put this in the equation. There are some little solities. You can take care of solities, and you get this kind of equation: x dot equals something, theta dot equals something. Sign effective velocity equation. This is your dynamical equation that comes out of that. What is this kind of so trajectories in phase space? What are these equations? You can plug them. This is the case without acceleration, but okay, plug them. It's very interesting. So these particles somehow, because of this equation, because of the interaction term that is there, a little bit more, they kind of get stuck with each other. This is the case phi is positive, like the linear model. They kind of get stuck with each other for a while, accumulate some time delay, and then when there's another one, they get stuck even more and then go different directions, and then eventually separate from each other, and then they have again the good velocity. So this is explicit trajectories of particles that represents this abstract kind of maybe formal way that I had to see the effective velocity, right? So soliton, in fact, one can think of that as being some kind of actual position of solitons in a dense soliton gas, where you don't actually see where the solitons are, right? You have a dense soliton gas, it's complicated, there's a field varies not kind of where you don't know where the soliton is. You can do asymptotic, then you see that, but otherwise you don't. But if you know the rho of theta and all that, well, you can approximate these positions by this model of reduction. How good approximate? It's just an approximation. You can define your position, so it sounds like that. Okay, but so this is just a model. What properties does it have? Well, it turns out that this model is not anything. It's a nice Hamiltonian system of classical particles. There's a Hamiltonian for that model. Hamiltonian is very simple, it's the energy. And the Poisson structure is a bit more complicated, but so the Hamiltonian simple, the Poisson structure has some complicated structure. The Poisson structure is obtained by using a generating function of the classical mechanics. So you define two variables y theta and two other variables xp. I was showing you the x and theta, so we kind of you put each of them a different pair, and xp and y theta are independently canonical. They are obtained from each other by some kind of canonical transformation. This Poisson structure without Hamiltonian generates these equations. It's a Hamiltonian system of equations. The reduction of GHG in some system of equations. Is it useful? Okay. Actually, to go, we can start. We'll make a connection with Hamiltonian structure of GZ itself that we have derived with
Can you show again what's the equation for E?
for E.
Yeah.
Yeah. So E was
You said the no equation.
sorry. So E was just the kind of the thing that determines the Hamiltonian. It's a function of x and theta. E is just some given function of x theta that determines the dynamics. Here we're saying, okay, so just if my dynamics is an arbitrary linear combination of constant densities with space varying coefficients, this is what my E is. But you can put any function x and any one there. And in this model of particles, you can put any function there. Is not Hamiltonian density, is no. But, yeah. So this is H before was an integral because I'm thinking about a model of exactly. Maybe anything, field theory, particles and all that, and I have my conserved densities which are continuous x. I can rewrite actually this E in terms of conserved density, but I've got to do a bit of work. So what is non-trivial here is that my E I write it instead of thetas, and thetas are kind of a bit non-trivial variables. Yeah. Which one? Tell me one. This one. Yeah. Sorry. So the small h is the small h is the eigenvalue of the constant quantity qi, the amount of that qi carried by the soliton theta. That's a small h.
But still, can you write this E? You said you can for soliton case.
Yeah.
How it will you show us?
So in order to write this, unfortunately, I'm sorry, I'm not going to push. To write the E explicitly, I have to say okay, KdV soliton gas, right? Then I have to write explicitly the quantities carried by our constant charge for every soliton theta. I can write that. They are the form theta to the 2n plus 1, the 3, the 5, that's powers of theta. So these HIs are powers of theta. It's also the case in the Liebniger model, they're just powers of theta. And in the end, this is kind of just a Taylor expansion of E in powers of theta. If you have just a finite number of constant quantity there in the soliton gas, you have the first, the second, the third, something like that. That's it. You just have three terms, and just 3 terms there, and the 3 first powers of theta. Yeah.
So I understand what this accent is.
Yeah, so theta is a spectral parameter that here, is the spectral parameter of soliton gas or the momentum you see asymptotically. Physically, like if I do quantum gas and I just look at the atom, it's very difficult to determine theta. It's an abstract parameter from abstract solution of the integral of the gravity or asymptotic parameter. So this is very physically sensible. These are conserved densities. I can write that. But when I write the E like this, it's a bit theta is more abstract stuff. So this should become some abstract model of particles. But indeed, this is the same Hamiltonian as that. Probably. Another question. It's kind of an observation that this generates the equation obtained after reduction of the GHG equation. if there is no external force, but if you take the hydrodynamic limit of this reduction, you become G. If there's no external force, then this actually model is UV integrable, not just something, it's UV integrable, factorized scattering, it has local interaction potentials. And in fact, the generating function, this phi that I use, has a very interesting structure. It's x theta plus some sine phi, where phi is a primitive of this curly phi. That is exactly the structure, what you see in the beta-ansatz wave function, if you do beta-ansatz negability. So the phase of the beta-ansatz wave function is a generating function for the classical particle system that maps real, positions and momentum to y theta. Y theta are kind of asymptotic coordinates. The phase of the beta wave function allows you to map real position and momentum to asymptotic coordinates in that picture. Yes.
When you say generating function, that's about the classical mechanics state. So
Yeah.
Generating a change of time.
Precisely. Yeah, precisely. So this is a mixed generating function that are 4 types. Yeah. So I would go from xp to y theta, say, and I write y equals something and p equals something. Okay. So this is classical particle models, nice property, connected to beta-ansatz. In fact, we argue that these trajectories are the trajectories of beta-ansatz wave packets in a finite density gas of a quantum, we say, using a model. If you have wave packets that go around, these would be the trajectories of these wave packets.
So related to the observation that you put that in classically and then to the reality. Classical level and then.
So I don't know.
Okay.
People that question, no, I don't know. Indeed, yes, good point. So I don't know where I like maybe investigate.
Feels like.
Feels like yes. Okay, we can discuss. Yes. Interesting. Other questions? All right. So suppose there's no external force. I wrote the equation in that way, x dot equals something, theta equals something. In fact, if there's no external force, you can explicitly solve this equation. How does it work? Well, if there's no external force, E is just a function of theta only. The Hamiltonian is just a function of theta. It looks simple. Of course, theta is a real variable, but it looks simple. And actually, maybe I should come back to. I was just saying. Yeah. So Hamiltonian function, it looks simple. I should rewrite it in terms of the more physical momentum P. If I do that, it looks complicated. Of course, it's got to look complicated because it has all these higher concept quantities. But the potential still has some nice property that it's a local potential. It's a complicated one, I cannot write explicitly, but it has locality properties. It's actually still a local model. The potential kind of encodes all these higher concept quantities in non-trivial way, so I can kind of evaluate them. All right, then so if E is just a function of theta, then the y variable evolves trivially. Because y and theta are canonical, and H generate the transportation. So y just becomes linearly evolved E prime times t, V is E prime. So initial and theta is invariant. So if there's no external force, theta are really fixed asymptotic momenta, and the y are kind of related to the impact parameters of the scattering problem. And then you look at these questions, the result can solve them. Here is solution. Y is related to x in explicit fashion. There's no t anymore, no derivative, nothing. So if you know the y's, you know the x just by inverting that. Now, can you invert this? You can if the sine function is regularized a little bit, and if phi is positive, maybe you can know the solution, but at least in this situation, for sure you can. You can invert that, Jacobian's positive. So once you know the y's and you know them, how to go there, you know the x, you just have to solve this equation. Turns out that this actually equation can be also solved by a convex optimization problem. And what this equation tells us is actually very interesting. It tells us that as you evolve in time, suppose y now changes linearly. Suppose the x are all separate, then there's no sign. So x then changes linearly, right? then eventually the x will collide. So then there will be this kind of positive function that appears there. And to reach that, you're going to have to advance the y for a while without changing the x. That's what's happening. And this was exactly the picture that I had there, right? They get stuck with each other a little bit. Like this one. And that means that somehow, geometrically, this phi, this additional quantity, is like some additional space that you've got to add. The particle is going to go through when it meets another particle. So there's a geometric meaning behind that. If you have two particles interacting, so one particle will feel an additional space, well, because of the presence of the other particle, and it's got to go through that internal space that you don't see by eye, but it's there, before it comes out. That's why they look like they get stuck with each other. And phi is exactly that additional space. It has the meaning of space, of the distance. So there is a geometric meaning. So once you account for that geometry, the particles evolve trivially. Once you account for this integral metric, particles evolve trivially. This is very nice, and you can do the same for the GG equation itself, and that comes maybe to the question. How do I actually solve this equation? I can change variable, which is what we call now normal coordinates, so this x hat is x plus something. And that something kind of account for the number of particles that you have to the 10. For minus infinity to x, and the additional space that you should account for this additional particle. And when you go to this new coordinate that kind of knows about all this additional space, actually this x hat is my y in the previous slide. Then the equation for rho hat for the density in this new coordinate is actually the Liouville free particle equation. So this transformation trivializes the GG equation with the interpretation that this quantity, this rho s, which is the denominator of the multiplication function, is some kind of density of space. How much additional space you have, this substratum is how much additional space you have where you can go through. You take into account that everything is free. It's like a gravity theory, right? Gravity, you just go free about the non-trivial metric. Metric depends on the matter. So the same thing here. There's a metric that depends on matter, on how much particles. And once you take out the metric, then everything is free. You can use that then to find explicit solution of the GG equation by quadrature. So this x hat then can be shown that to satisfy itself a nonlinear equation, which turns out to be a Banach fixed point problem in the Banach space of bounded functions. So this has a unique solution. There exists a unique solution. And once you have that unique solution, then you construct your rho specifically. Okay, I go quickly, and then so there are theorems one can get out of that we developed with my student, the Kubner. And what we can show from this is that actually the GG equation, under certain conditions, there always exists solution to the GG equation, even if there are initial discontinuities. So the weak solution exists and is unique under weak condition. And if the initial condition is differentiable in X, then the solution stays differentiable at all times. No shock error developed. It's very different from the standard hydrodynamics where you have shock development. So smooth initial condition gives smooth solution at all times. Smooth solution exists and is unique. Yeah, okay. And oh god, I wanted to talk about do I have another 2 minutes? I started late.
You started late, yes, so.
3 minutes.
Just because it's you.
Okay, so the last thing I wanted to say, which is the most exciting bit, unfortunately, of the talk, is that one can do all that also in higher dimension. And we've been working on this now with DL, people, which I will cite hopefully here aside. TP equations, equation in two space, one time dimension. It's integrable. And one can ask, well, what are the stable objects? Well, in certain regime, the stable objects are line solitons. So these are, here's a picture of numerics, non-major common. And you see that certain regimes here, you see that you have lines, structured lines which are stable structures in 2D, right? And these lines, when they interact, I mean, when they cross, they kind of have a little phase shift in 2D. It's not in time, it's 2D. one time slice. When you, yes,
Sir, type on your CD.
maybe,
It's mostly less.
yeah, there's a Y somewhere. Sorry, yes, Y, this Y. It's like X and Y, yeah. Okay, so 2D. And it's very interesting because these solitons, they have, okay, they're stable, when they cross, there's a spaceship, and the time function is relatively simple. They displace linearly in time. So the structure we have is that we have line soliton with shifts in X. Say I can think of that as in Y, or shifts in X by phi. Some slope is stable. Some linear displacement with some velocity that depends on the models. I have now theta characterizing my solitons. In fact, I mean need more than just one real parameter, right? So this depending on the model, not that. So this is X and Y, this time function. This looks a lot like like what I was showing before, but the trajectories. The idea is you take the trajectories in space-time, you look at that in X, Y, and then you put a new time function on that, which is a shift of the impact parameter. And this is what I wrote here with these equations. It's just taking these naive ideas, turn them in equations. That's it. So this is kind of the GG equation for 2D soliton gas, if you wish, in terms of some quantity, which is then linear density along X, has an equation in Y and in T. And you can also think of this in terms of this atomic reduction, where you have new Z variable that linearly evolve in T. Okay, that's all I wanted to say. So there's a lot of models that have been analyzed with GGD, divide, there's a lot of stuff that have been done, correction functions have been evaluated, diffusive corrections, work with Prof and our students. We now understand more free the diffusive corrections, the fluctuations, and there are many reviews, and here I cite some of them. Thank you for your attention.
I'm conscious of time, so I'm going to take a couple of short questions now because there are already quite a few, and we have a coffee break anyway that to carry. So tomorrow.
So it is with some role. There is a standardized state.
For the hardware state.
Yeah.
Yeah. So you can ask what are all the possible stationary steps.
Yeah.
There are many of them, and supposedly the ones that are clustering in space and stationary are the ones where you place the rod in a Poisson way, so independently in space with a distribution of the velocity, which is the same for every rod. That's stationary state. Microscopic stationary state, stationary in space and time.
My question. If I take a hit state and the rod doesn't work.
So the
Yeah, but we are meeting hit states, so we
Yeah.
are meeting configuration.
Yeah.
I think a rod that is not a hit state.
yes.
Which of these state?
So which of the state will you go to, or
Yeah.
So this is this is a non-trivial question. It's a question. So if you take some state which is far from being stationary, so anything, what you've got to calculate is calculate all the conserved densities of quantities in that state, and we know that these are fixed in time; they're conserved. Then you let your state evolve, thermalize, and then it will go to the GGE, which has these values of conserved. That in principle fixes precise distribution velocity. So that's a general thing. I mean, for the rods, you basically you look at how many rods you have of velocity v for every v, and then it will go to the state which is distribution, the corresponding distribution of these velocities, and then kind of flat distribution of space.
You have to actually, you can see.
Yeah. People have done numerics for that. Yes, I think so. Yeah. Sure, it would be proven on that.
Very general, but hope we could answer short because we short time. So for this generalized hydrodynamics, you showed some models like rods and this here, but are there examples where really it provides in some sense, some reasonable sense satisfactory solution for some unknown answer, I mean some unknown system just so full hydrodynamics?
So
Available or not?
so I'm not sure what you mean exactly. So I can take any of
For example, you know, like, let us look an example, hard rods, which of course is a well-known system.
Yeah.
You can do numerical simulations,
Yeah.
right?
Ah,
Monte Carlo, and then
Yeah.
just this equation from generalized hydrodynamics,
Okay.
all would satisfactorily agree with
Yeah.
kinetic Monte Carlo.
Yeah.
Such examples,
So
for example, can you give just name?
So it is of course hard to do with Monte Carlo, you can do for hard rod easily, for quantum model is much harder. It's much harder
Not
to
one,
check.
any not one.
Classical models, I'll be available the models that I don't know about the check the hydrodynamics. It does agree with GEG for models. I always agree with GEG, but one always is able to calculate various things. I mean, well, it's hard to prove that it agrees with GEG. However, this possible. To the model. To the model with differential interaction, there's no proof that this should go to GEG. But calculations are very but no. But then you can do the numerics, calculate various things, densities or correlations, check against GEG, and it works. In that sense,
In the limits, or just translation.
so depending what you want to do for correlation functions, you do that in stationary state, or you can do something like start with a state which has a lot of particles there and less there. The human problem, right? Partition particle that it evolves, and then after a bit of time, you wait a bit, but not too much. There's a distribution, and then you compare with GEG, and GEG describes distribution of particles or also quantities in space and time.
I mean, it's worth like completing, so we're very happy.
So, works like, you know,
magnitude.
the corrections, what is the amplitude of corrections is a combinatorial problem. You expect maybe some powered up corrections or something like that, but it works very well. The longer you wait, the better it works, because you approach the taxation better, but it works very well. You know, to prove the statement of GEG is an actual limit, the roller scaling limit x t large. You can write it mathematically in the statement. Then you should check that numerically is difficult because you've got to take a limit. GEG only valid in the limit. Large spaces. But it turns out it works pretty well even from quite early time.
I think we should thank Benjamin again.